So when you are tasked with doing defense and you have a security incident that you need to investigate, your investigation is really only going to be as good as the recency, relevance, and fidelity of the artifacts that you're able to collect. So when something happens, you need to get information as soon as possible, and you need to know where to look. So my name is Matt Benyo. I work on the Jamf Threat Labs team with Jaren and Sal, who spoke this morning. And also I'm joined by Stuart. Stuart had a last-minute emergency. He wasn't able to make it. So we've captured his soul and embedded it within this keynote where he will exist for many, many years.
Thanks, Matt. In our work at Jamf, we specialize in writing detections for macOS.
So Jamf, as a company, we make other products, obviously, other than the Jamf Protect macOS detections that we do. And these products enable teams to remediate and respond to the detections that we actually deliver to them. But really, the response, other than things that we're immediately blocking, is really up to the customers or whoever they've outsourced that responsibility to. And in many organizations, whoever is at the console, that responsibility has been outsourced to them. So as we know, in many cases in organizations, especially smaller organizations, admins are tasked with security responsibilities. And if you think of an organization like a school, a lot of times admins aren't going to necessarily know how to interpret certain types of alerts. So in our work, while we're building detections, occasionally we'll receive these types of alerts from our support staff, and they are talking to us on behalf of a customer who had an alert and looking to know what to do about it. And if the support person doesn't know how to interpret that, they'll come to us. And obviously, it's not outside the scope of what we do, but obviously we want to do what's best for our customers. So we get into a conversation, we give our best guess to support takes it back to the customer is taking that to an end user, and back and forth, and support staff is caught in the middle, and really it's a terrible experience, especially for the support person. So to make matters worse, in the times where we do really get involved, honestly, a lot of the times, by the time we're helping the customer, it's been days or maybe weeks until the event happened. And so the quality of the data we're able to get back is very low. And obviously, the customer doesn't always understand how those limitations work either. So we decided to take matters into our own hands and went looking for solutions. So one of the first things we found was a tool built by CrowdStrike called Automactic. And these are some of the modules that they have. We took a lot of inspiration from those modules. But one of the drawbacks was it was built in Python. And since Python is no longer natively installed in systems, we felt like we needed to iterate on what they had done.
We also found another tool called Venator. It's an open source Swift project from Richie Cyrus. Richie was actually my inspiration for getting into blue teaming when I met him at the first Objective by the Sea. When he initially made it, he was at SpectreOps, now at Apple, and unfortunately it hadn't been updated in quite some time. Ideally, what we were looking for was something lightweight that could be installed on endpoints and be on standby for an automatic on-demand execution and collection at the moment our detections were being fired. This would minimize unnecessary collection and accumulation of data, but would also ensure the freshest possible snapshot of the system for instant response and investigation. We mentioned that we wanted something native and didn't involve installing something like Python on every system. We also wanted to make sure it was performant, A, because the faster it runs, the fresher the data is, and B, it would be an added bonus to be able to run it in the background with no apparent system slowdown for the user. So it's fast, it's maintainable, it's native, and it gives us the most access to built-in APIs that allow us to really customize exactly the data we wanted to collect and analyze. And frankly, we know it's a bit of a flex, but we've staked our business model on our Apple expertise, and what better way to demonstrate that we understand the platform inside and out than building something dope with Swift. So we created Aftermath. Aftermath is a Swift-based open source IR framework designed to capture all the artifacts that are necessary to a proper investigation. Then, subsequently, to analyze the relevant data to determine the threat vector used as well as how we can best remediate the threat.
So Aftermath has two primary components. The first is the collection side. So Aftermath runs on the endpoint and collects as many cool and useful things as we could think of. And then second is the analysis. So for the most part, getting a bunch of data is the easy part. And we wanted to make it easier, especially for less experienced teams, to extract meaning from that data. And we also know that even for teams that are more experienced, it can be really time-consuming to make sense of a bunch of data that you've collected. So we have taken it a step further. So for the collection piece, we feel that our collection feature is really robust. We've got about a dozen modules that are broken into their own classes. So we have things like we gather persistence. We also look for process information of currently running processes. We do a lot of unified log searching. And we also collect browser data. And then beyond that, we also collect, do a system recon, which we'll talk about in a moment. And then we collect some more general artifacts on the system. So one of those more general artifacts would be something like the TCC database. We capture a copy of the TCC database. And having that gives us the ability to check out all the apps and the services that have been requested and granted special permissions on the system.
We collect relevant browser information like history and downloads to be able to determine potentially where the threat originated. This can help you discover how the threat landed on the host machine. So say we have the user's browser history, in this case from Firefox. We can see the user went to ponzi.com/downloads, then had to Google help I'm infected, ended up at Objective-C's website on the products page. It must have worked because less than half an hour later, they Googled how to thank Objective-C, and then looks like became a Patreon subscriber. So what we could do after we have this information is potentially visit this website. We could simply just copy and paste it and put it into the browser and visit it to see what it is.
And in this case, it's a potentially unwanted program called Ponzi. So in my opinion, one of the most useful pieces is the collection of methods that we've dubbed System Recon. So System Recon is a feature that tells administrators and security professionals a lot of useful information like Xprotect versions, airdrop status, firewall, system integrity protection, as well as things like file vault being enabled, screen sharing. A lot of those things that you would check, we gather that all in one place, including things like environment variables.
So once we have all of this data, both in raw and lightly parsed form, we pivot to analysis. So analysis is typically performed on a different machine than the victims. We will gather the relevant information. We can put it through an MDM or simply extract it, and then bring it to a host machine for analysis. This brings us to what we get in the end, which is a storyline that tells us the entire story of the malware. So what is this story for a new piece of malware? So say we were just a user and we wanted to download Final Cut Pro to make some overproduced TikTok video. But at the same time, we don't want to drop the $300 it costs to buy a license, so instead we elect to pirate it. Not an uncommon thing to do, and also not uncommon to get a bad case of malware while you're at it. So we navigate over to Pirate Bay like it's 2010 and find a slick, cracked version of it. We download this using something like Transmission. We mount the disk image that it arrives on our disk with, and then inside that is the application, and we go ahead and install it. Little did we know, we got owned.
So the other thing that we didn't know is that when we downloaded this Final Cut that was cracked and launched it, we were also launching a Bitcoin miner. And this is a very sneaky piece of malware that we encountered. We found that this Bitcoin miner, when your fans fired up, if you went to the activity monitor to check what was going on, it would actually kill the miner, so you wouldn't be able to find it. So we eventually get suspicious, or in our case, we triggered Yara detection. And so it's time to use Aftermath to get to the bottom of what's going on the system. So we can either do this straight from the terminal, or we can actually use an MDM. So to take a brief detour into MDM land, There are actually some really cool advantages of using MDM for this. Obviously, we can use this to scale it out. So this doesn't have to be used with Jamf products. This is an open source tool. So a lot of these pieces are available in different products as well. But the idea is you would have this running on your different endpoints, and you can essentially automate the triggering and collection of this thing. So for example, if you run it from terminal, you're going to need full disk access. But the cool thing is if you trigger this from an MDM, you actually run with the privilege of the MDM, and so none of that stuff is required. So just to show a brief demo of how this can kind of fit together, let's say for example, we're just running like a reverse shell on a victim machine. So the reverse shell runs, it's going to trigger a detection in Jamf Protect. That detection then puts this computer within a remediation group within the MDM, as you'll see here in a moment. Sorry, switching to that tab. So it's in this remediation group, which kicks off the running of Aftermath immediately upon this detection. And that collection happens, and the data is then uploaded to Jamf Pro. So you can see, we have even the details of Aftermath running. So maybe if there was something that didn't run properly, we have all that output available to us from IT or security. And then if we go into the inventory record, we actually have the output of that file uploaded to the cloud, so we don't even necessarily have to talk to the user about it. So we can do all of our analysis right then and there, and that data is going to be as fresh as possible.
In our case, we ran it from the command line. You can see, using that deep argument, that we're actually scanning the entire user's home directory, collecting the timestamp metadata on each file, as opposed to just the default directories that are most commonly associated with malware. Fortunately, I've had on good authority that this miner actually does a lot of its nefariousness in the user's application support directory, whose timestamps we actually collect by default. So for the sake of this example, we can ignore this deep argument. You can also run the collect DIRs argument and actually dump the raw contents of whichever directories you pass it. So if we wanted to actually grab all the files from temp and downloads, we could. Of course, use this at your discretion, because heaven forbid the user just download the latest Xcode beta and has a nice 8 gig file in there. Or maybe they just haven't cleaned up their downloads since 1970. In the case we run directly from terminal like this, we get a nice output of what Aftermath is doing. We can fast forward through some of this, so we can actually get to what I think is one of the coolest parts. Now, once all of the collection details are on disk, let's take a look at what we've collected. And pretty simply, we can either do this from the command line or directly from Finder. If we pop open the folder in Finder, we can then unzip that archive and dive deeper into the data.
So these are the raw files, but we can actually do a bit more with this with the analysis function of Aftermath. So if we take our zipped up contents and pass that as an argument to the program running sudo aftermath analyze, we start to get this analysis happening. So Aftermath will start analyzing all the data that's collected, and since we didn't specify an output location, it's going to land here in the temp directory. And we can see some of the different CSV files that are generated here. And so we'll start with one of the two databases, which is TCC. So if we pop this open, we can actually see the parsed and translated content.
We can see that when we parse the TCC information, we get the most important information back. We can see which client made the request based on their bundle ID. We can also see what service they were requesting, whether it was full disk access, the address book, or different folder accesses, or even things like the camera and mic. We can see what happened. Was it allowed or denied? And of course, we can see the reason. So was this set by MDM? Was this user consent or system set? This all maps over nicely to this set of enums here that we actually have in the database. It's compiled from a different source. But if you scroll through these, you can see it's quite robust in how we map these over. Of course, lastly but not least, we can see when this was last modified, which is really important when we're parsing the output. For example, we can see that this app called QLab, based on its bundle identifier, which is used for making audio cues, we can see that the camera and mic requested access right around the same time, and that the user, me, denied the former and allowed the latter.
So one of the unforeseen challenges of this project was the scattered nature of the different timestamp formats in macOS. So some of the databases and apps use Mac Absolute Time, others use Epoch, some use local time. So in this process, we standardize all these timestamps so that we can accurately organize everything into a chronological storyline for analysis. So going back to our example of the Final Cut Trojanized with a miner, Aftermath did its collection after the miner triggered one of our Yara rules. And let's take a look at how Aftermath is able to piece together this story, collating these timestamps of these different artifact sources. So once we're looking at this file in this timeline, a few things start to jump out. We can see we've got in the Safari history, we see the visit to the Pirate Bay. Up a few lines, we can see clearly the download of a torrent. And then further up, we can see evidence of the transfer taking place of that download. And as we move further up, it starts to get a little bit more interesting. We start to see some unusual activity in the application support directory, so this I2PD. So when we initially found this, we didn't know what this was, so we looked into it, and it turns out I2PD is the I2P daemon. So I2P is actually, lesser known at least to us, an anonymous network layer that allows anonymous end-to-end encrypted communication. So this malware was doing all this crazy encrypted activity in the application support directory. So even if the admin isn't necessarily able to make sense of this data, when they get a hold of someone who can, they're going to have valuable and relevant data to share that is timely.
So looking forward, what are some things we want to do with version 2? I think it's important to kind of have these mapped out. So first up, we want to allow and integrate uploading of the collection and analysis files to S3. We want to collect the extended attributes of different files, especially files we're collecting. And also pivot off p-lists. So if we collect a p-list, say this one for block from Objective-C, we want to be able to reach out to that exact location of the binary and be able to pivot and grab that as well. Those are a few things we're looking forward to coming up. So that's a little about how Aftermath is going to change the IR game for Macs. It's in Swift, performant, and helpful to anyone responding to a threat, and is open sourced today. So feel free to check out the Aftermath project on GitHub, and it is available now.
So, sorry, just a couple of acknowledgments. So Stuart really took the lead on this. He was definitely the lead developer. Our team definitely contributed. Maggie, who's also here, was definitely a major source of help on some of the Swift stuff. And also, shout out to our sensei, Jaren. We took a lot of the ideas in his book, OS and Incident Response. And as I already spoiled the surprise on this one. So again, the link to the GitHub if you want to talk to Stuart about any of the coding stuff. But when we started this, it was really just kind of a ambiguous on the clock, off the clock kind of passion project. And in honor of the ASCII art that we were not allowed to show you, I thought I would just provide the notice there that was told to ask us to take that down. So please check out the GitHub. We welcome your feedback and any contributions to that with pull requests. Thank you so much.